Okay, this is Scott. So I'm going to be doing a brief demonstration on TMPCA, which is time-wise multi-way principal components analysis. It's related to PLS, partial least squares, as well as principal components analysis. So the example that I'm going to talk about was based on a case study by Namicus and McGregor. So I have essentially two different data files, but overall the data comes from an industrial batch polymerization reactor. So the batch duration is approximately 2 hours, and it's divided into 100 equally spaced time intervals. So at any time interval, 10 process variables are measured, as you can see here, variables 1 through 10. And variable 1, 2, and 3 are temperature measurements within the reactor. Variables 6 and 7 are temperature measures in the heating cooling medium. 4, 8, and 9 are pressure measurements, and 5 and 10 are flow rates and material added to the reactor during batch operation. So for a single batch, there were 100 readouts of 10 measurements. So here I have the batch number. So there'll be 100 batches here for B1, and again the 10 variables. So the original set had 55 batches, and 47 of these were considered to be successful runs, in other words, acceptable polymer quality, and the rest were either bad batches or batches with qualities near the borderline of tolerance. So the good batches are batches 1 through 37, 39, 41, 43, 47, and 48, and the borderline batches are 38, 45, 46, 49, and then the unsuccessful batches are 40, 42, 50, and 55. So this example right here, this is basically a good set. So if you look at the value statistics, this is 1 through B1 through B30. So these are all good batches, and that's what I'm going to use to develop models, and then I'll use the other batches to score. So our objective here is to apply TMPCA time-wise multi-way principal components analysis to the normal batches file, and then we'll score against a different data set that contains some of these other batches. Some of them are successful, some of them are not successful. So the first thing that we want to do is we want to create the model itself. So what we'll do is we'll go into statistics, PCA here, and then we'll do time-wise multi-way principal components. All right, so I'm going to click OK there. So I get the different tabs across the top. The quick tab is the variables tab, so I'm going to grab variables here, and the variables that I want to grab, I'm going to put time in here as my time variable, variable 1 through 10 as my continuous variables, and then the batch number will be my batch variable. So we have that there, and then some of the other settings that we want to do here. Let's see. So one of the things also that I could mention is on this variables tab, if I have categorical variables, then statistics is actually going to form some dummy coding in the background. So those dummy codes will be treated as normal variables in the NEPALS algorithm. So that coding's done for us. And then the algorithm itself, I can set the number of iterations that the algorithm will go through, and a convergence criterion. So if I converge before the iteration stops, then the algorithm will stop. If not, the maximum number is it's gonna loop 50 times before it quits processing. And then the fitting, I can select V-fold validation. That's actually by default is what's done with 7 folds. So I'm just going to set the seed. This seed comes up by the clock by default, but just to get similar results, I can set a seed within the platform. So I'm going to set that seed as 7 here. So the number of components that are going to actually be selected is going to be set by the algorithm, or I'm sorry, the V-fold cross-validation. But I could also set the number of fixed components if I wanted to do it that way. And then lastly, we could rescale or choose not to scale the variables, but here we're going to, by default, we'll use unit standard deviations here to set the defaults. And then we can also handle missing data as well. So you can set these parameters. The default is 80%, so we'll just go with the default there as well. So I'm just going to go ahead now and run this. So results come back pretty quickly, and I get, by the V-fold cross-validation, it actually comes up with 5 different components, and I can look at my R-squared for the X and the cumulative R-squared. So for the first component, I get almost 40% for the R-squared, and these are obviously in descending order. So the most important component is listed first, and then cumulative components. So for the 5 components, I explain about 69% of the variation based upon these 5 components, and then the related eigenvalues, which tend the same direction, right, as the R-squares, and then the Q-squared and the limits, and then you can even see here the number of iterations that the algorithm has gone through to select these different components. So then we can do quite a bit within this panel to look at the different values and everything. So one of the things that I could do is I could punch the summary button, and essentially that's going to give me the same display that we were just looking at in the default. One of the other things that I can do is I can get a plot of that as well. So if I hit summary overview, well, it didn't give it to me. So this is basically a graphical format for the R-square of the X's and then the Q's. And the important thing to note here is this scale is starting at 0.3. So it is essentially the same information in a graphical format. Another thing to note here is that I can actually add components here. So if I were to add a component, here would be my 6th component here. So you have some flexibility over here, or I can remove that component as well. So you can add and remove components as well. And that just gives you some additional functionality. So again, we're using the algorithm to determine the optimal set of components by default based upon our configuration, and we came up with these 5 here. The other thing that we could do is look at the variable importance, which is useful in PCA, and it determines how well a variable is represented by the principal components. So this is often expressed as power, and it's a number range from 0 to 1. So for a mature model, a model with sufficient number of components, variables that are not well represented have low power and are likely to be insignificant. So what we need to do is click the variable importance to get this, and we express each one of the variables. Remember, we have 10 variables, and the power, and then the rank. So the first variable is the most important, 81.7%. Very close is variable 2, 81.4%. And then they kind of drop off pretty drastically from 2 to 3, but still, you know, fairly important within the different components within this spreadsheet that you can see here. And if I wanted to get that within a graphical format, I can do that as well. I can come up with a variable importance, and so this is essentially a graphical representation of what we just looked at. And then, you know, one of the most important things is the hoteling T. So if I can get a T-squared chart, well, and so I can see here that all batches are well below the limits of tolerance, which should come as no surprise since the data set contains only the successful batches, right? So we only looked at normal batches, batches 1 through 30 in this model building. In other words, a normal process, golden batch, whatever you want to call that. So further batch diagnostics can be carried out by using scatterplots and T-scores. T-scores are transform values of the process variables in the principal component system. So, you know, a T-score too high can again be regarded as a representation or denoting abnormality. So to generate the T-score scatter plot, we need to go back to the analysis panel, and then we need to check this tab from quick to plots. And so by default, it's going to select component 1 as the first and component 2 as the second, since those are the most important components in the analysis. And then, so what I can do then is I can just click on a scatter plot, right? So the scatter of the T components gives me, you know, what that looks like. And actually, there's one other configuration that's kind of nice. If I click, let's see, let me find it. So it's going to be a warning label. So if I check this box right here, and then I click that T again, then I'm actually going to get a warning. So, and I can have brush control as well. So I can look at the different components from that is one way that I can look at that. Another thing that I could do is, there's one other configuration that I'd like to do. I would like to, let me just close this. I would like to check this display text labels and do that one more time. And then that gives me the different batches. So, and by the way, and I can brush and I can drag these labels around and everything. So you have a lot of basic statistical or statistica functionality. But here we can see that 2 batches are beyond 2 standard deviations, B22, B14, but they're all within 3 standard deviations given here. Another thing that we might want to do here is look at the contribution plots. So if I do that, I essentially get the contribution from each variable, and this is on B1, right? So this is for B1, and then I can look at different batches. So if I were to look at, say, B2, oh, where is it? Okay, B2, and then I were to look at the contribution chart for B2. I can look at these, and I can basically look through my analysis and look at the different contribution scores depending on which batch that I'm actually looking at. And so that's kind of nice. And I can look at the different components as well, right? I can look at, so I just moved the batch, but I can look at the different time code and the different components. If I move this to 2 and I were to look at B2 and then I were to get a summary of that, I can look at the significance there as well. And then what are some of the other things that we want to do? Oh, one of the things that we might want to do is a trajectory plot. And to do that, I'll want to go to the Advanced tab and look at the trajectory plot here. So let's just select batch 1 here, and then I can do this across different batches. But this gives me, you know, again, we had 50 periods of time for this particular batch, and we can look at this here. Another thing we can do is look, you know, we can zoom in with that. We can look at the different points. So you have that ability to, you know, look at the different analysis, zoom in, see where things were there as well. Okay. And so one of the things, now that we've built a model, if we're happy with it, we've analyzed it, what we can do is we can bring our model back up, and then we can save it. So I can create a PMML script. Here is my PMML script that goes along with the model that we just created, and I can save that model off. So here I can let me see, like I was about to do. So let me save item as, and let me just stick this into just a temp file, and I'll just call it model here. So I'll replace that, and now I've got my model for this particular analysis. And the next thing I might want to do is that model against a new set. So I'm going to minimize these, and so how do I do that? Obviously, if you're scoring a new batch, and you didn't have this open, you just open up the panel like we did originally. They've already created a model. I'll just cancel this, and then I get back to the startup panel for the process. And then I can click cancel again, and then I get back to my way. Again, I could start this from the very beginning. So, and then what I want to do is I want to deploy, which is on the same panel here that I had before, but instead of selecting this one, I'm actually going to do deployment up here, and I'll click OK. And then I want to load my model in. This is the model that we just created, so I'll open this model, and that's going to take that PMML code and, you know, reference it for new batches. So I'm going to locate the batches, the batch data that I want to score. This is the normal batch data. This is the one I used earlier, so I'm going to close that, and then I'll bring this, which is the batches for deployment here. I need to go back. So you need to edit out that previous part, and then what you need to do is 1, 2, 3. Okay, so once we have that model created, we can go back to the panel. Oops, excuse me. Okay, so the next thing that we want to do is we want to pull from our examples file that comes with Statistica. We want to pull the batches for deployment file that we've discussed. So I'm going to double click there. I'm going to go back to my PCA, and this time I'm going to select the MSPC deployment. I'll click OK. Then I'm going to load the PMML that I had previously, which was in here. So this is my model that we created earlier. So once I have this, I can look at the model summary, and I can actually create predictions with this particular data. One of the things that I might want to do is come up with a t-squared chart for this data. Let me do that again. And then I get a chart that looks like this. So again, I can enlarge this a little bit. I can expand my view, but obviously we can see here that there looks like maybe a point here is almost out, but not quite out. But definitely these points right up here are. So we can note that these batches 50 through 55 are very different from the rest, and they possess extremely large t-square values. So they're definitely not normal batches based upon our traditional process. So then what we might want to do is create some t-squared line charts as well. So what I can do is, so one of the things that I might want to do is, again, look at this t-square, and I'm going to look at for component 1. So this is the drop down. So the first one we'll do is component 1, and then we'll do component 2, and then we'll do component 3, and then we'll do one more component. Let's do 4. All right. So if we look at these different lines, we can see that, you know, from the first one, from this first graph, that there's definite signs of abnormality here for batches 50, 52, 3, and 4 of this plot. And then we can look at some of the other plots as well. Definitely batch 50 all the way through 55 here for the second plot, as well as the third plot, and then the fourth plot. We can also look at this distance to model. So this is another chart that again shows that these last batches are very, very different from the previous batches. They're unusually high, and something definitely is going on here. And then we can look at the contribution plot as well. So I can look at this, the score contribution, and look at variables 4, 9, and 10 here. Pause. So yeah, the contribution plot shows that I can definitely see this is going to be, I created this for batch 50 right here, right where the process started going odd. And so I put batch 50 in here, and then if I look at this plot, I can see that variable 4 and variable 9, something is really going on there. So what I might want to do is, at this point, generate a time scale. So what I want to do is I want to look at the trend or the evolution of some of the process variables, and so I want to look at a time trajectory on these variables and look at those. So what I can do is I can bring up my analysis panel again, and then since we notice it was variable 4, what I can do is I'm going to do a trajectory chart, and I'm going to select variable 4, and then see what that plot looks like. Again, I'm going to do this for batch, say 50, and I get to see what's happening out here within the process. And let's do the same for variable 9 on 50. And I can look at the relationships there as well. So we can definitely see drift from this variable 9 here for batch 50, well above everything, well above the average, and then drops well below the average here for this time for batch 50. And then as we saw for variable 4, it was really low for batch 50 compared to the average, and then kind of goes off here as well. But quite a bit of difference there.